In this session of the Caesar 2 Statics online video training series, we'll discuss restraint definition in Caesar 2. Now, if I was presented with a drawing for analysis where I had clear symbols on the drawing or schematics that indicate what type of restraint should be in the model, it would be very simple to model these. If I have this symbol, I would consider it an anchor. All 6 degrees of freedom are restrained from motion, and in Caesar 2 I just put the anchor at that node. If I have a symbol for a double-acting Y restraint, clear enough, just put a Y restraint in both directions. Or a resting restraint, easy enough to put in a plus Y restraint in Caesar 2. These are quite simple. Unfortunately, a lot of times when you're working with building your model, you're not presented with a clear analog to work with. We might have a picture like this, or the actual physical device in the field like this. So what type of restraint is this? It depends how important a good restraint definition is. If I'm close to a piece of rotating equipment, I want to get a better model for this restraint. If I'm out in the middle of some rack piping, it's not that important to have the exact model. But you must keep in mind too that whenever you are making assumptions in your model, it's up to you when you look at the results to confirm that your assumptions are still correct for the analysis that you're looking at. So, if I look at this system here, I might say it's just a guide, no gap at all. I'm only worried about the horizontal direction. If the pipe moves up too much in the vertical direction or down too far in the vertical direction, I would find that in the results, and then I might have to add a Y restraint as well. If I consider this gap here, personally I would not get involved with gaps this small. They're not in there for design for engineering purposes. They're in there for clearance. It's just construction gaps. So somebody though might put in a guide with a gap and figure that is a better model. It might be a better model, but it might be inefficient in time savings. Or let's say you don't want to check how much it moves vertically. Go ahead and put a Y restraint with its own gap on it in the vertical direction. So here are 3 possible models, and all could be justified or defended, but which one do we want to use? Which is the right one? And I think that's probably the real important thing here, because in many cases there is no one right answer. But it's up to you again to check those results to make sure it's appropriate for your loads on your model. I'll say this, the greatest source of model variation lies not in the quality of the pipe length and the OD and the wall thickness and temperature and pressure, but it's in the definition of these piping restraints in your Caesar 2 model. So it'd be important to get a good handle on defining these things and be able to defend your approach. Now if I look at my Caesar 2 definitions for restraints, this table here pretty much covers all the restraints that are available in Caesar 2. The restraint must have a vector. They're all in a single vector except for the anchor, which is all 6 degrees of freedom. And basically they're in a global direction XYZ or rotation XYZ. The other approach you might take though is that, well, what if I have a restraint in some odd direction? This restraint here is in the horizontal plane on a 30-degree angle, where I can use any number or any letter like X, Y, or Z, and if I follow it with 3 numbers in parentheses, this will be taken as direction cosines, and it will trump this Y. So this restraint is not in the Y direction, it is in 1/2 in the X, 0 in the Y, and 0.866 in the Z. So you don't have to follow the global directions. You can find any vector you wish. You can also put a sign on most of these restraints, and these make them single direction restraints. And we discussed that many times throughout these video series. The plus Y restraint is a resting restraint, and we can work with these signs to make them work in one direction and not the other. These are these nonlinear restraints. All these restraints have some sort of stiffness associated with them. If you do not enter a stiffness in the stiffness field, the program assumes it is a rigid restraint. And we put in a very large stiffness for these rigid restraints, 1e to the 12th. It's very difficult to structurally create that much of a strain. But you must remember that in pipe stress analysis, historically, the only interest in evaluating the systems was evaluating them for strain. And to be conservative with regards to strain, in most cases, being more rigid is more conservative. So again, by default, Caesar 2 goes to 1e12, a very, very large number. Then, if you wish to get a more accurate calculation of that stiffness, or more accurate use of a stiffness, you could use other tools to type in your own stiffness that you wish to use. Most users use our rigid stiffness. Now, based on the type of restraint vector you're defining here, you have these other modifiers. And that's the nice thing about the windows. If I have an X restraint, I have this set of modifiers. If I call out a rod, I have this set. So the input screen is updated automatically to reflect these modifiers. Now, when we talk about restraints here, we're talking about boundary conditions that are defined by restraints. There's another boundary condition in Caesar 2 that works just like these, would be a displacement. So you might have a bunch of individual displacements defined in your model that you could reference as well, but we're talking now about these other types of restraints, not displacements. So if I look at my input screen here with all these different types of restraints, to get access to these, I will click on the restraint checkbox here on the element 15 to 20. I say I got a restraint, and it'll open up this field here. And here's where I can define the node number, the type, that'd be this vector here, connecting node if I need one, and then the gap, stiffness, and mu. That's this set here for the most typical restraint, a translational restraint. Now, there's some items here that get a little bit complicated, and I just want to review this very complicated one here by breaking it down into two separate approaches. Firstly, let's look on this side over here. If I have a Y restraint, I basically don't have a sign on it. That means it works up and down. This restraint is against deflection in the plus and minus direction. If I have a plus Y restraint, it is preventing negative Y motion. Now this is, I'll admit, a bit confusing. When you think of a plus Y restraint, you would think it might be on the positive side in the Y direction. But this is the industry standard here. When I say a plus Y restraint, what I think in my head is the pipe is free to move in the plus Y direction. So it is free to move. This definition has no restraint in the positive Y direction. Now, let's look on this side. Here's a guide or an X restraint, using X direction, an X restraint. It can't move either positive or negative X. If I wish to put a gap on it, I can define a gap and it will pull the restraint away from the pipe. So the way I interpret this is that the gap must close either positive or negative before the restraint becomes active. So now we have the two components that allow us to define this very special case here. So what type of restraint would this be? Well, the pipe is free to move in the positive X direction. So I'd have to call that a plus X restraint. But if I look at the gap, this is a gap that must close before the plus X restraint becomes active. So again, you find out what direction of free motion, that'll define the vector there. Here it's plus X, and this is the gap that must be closed before it becomes active. So that's the introduction of this section, and what we're going to do for the remaining part of this presentation is go look at specific examples of different types of restraints, identify the modeling that will be used in Caesar 2, and also point out some modifications that might be important in adjusting that model.